Okay. I guess we're 1 minute early. But by the time I get my head together, we won't be 1 minute early. And open my chat window. Well, that's a nice optimistic chat going on. Yeah. I have nothing interesting to say about that. Yeah, just this term rushes by. It gets better. Every other term is better than this one. It's all the nice things I can say. So in the absence of saying nice things about the term, I did get a question about talking about some of the eliminations. I did promise to come back to them, and I think I covered them in the lectures. And somebody said, well, hey, can you talk about these eliminations that are oxidations and the oxidations that are eliminations? So I can start there. And if anyone's got questions about the radical stuff, we can go there. And we can also, if there are any other specific questions about SN2, E2, SN1, E1 as it's starting to sort of sink in, we can discuss that too. But maybe I'll start with the mechanism on one of the oxidations. So let's say we had when did I say? Next week. Why? Because we put off another one and it's closer to finals, and this one's a pretty early final, so it all makes sense to study for it. And yeah. So let's say we're using the Jones reagent. This gets expressed in a few different ways, so we'll do it the hardest way. And when we were talking about doing this, when we were back at the carbonyl chemistry things, I was saying, look, with the primary alcohol, this is going to oxidize all the way to the acid. I said, don't worry about the mechanism now, because the mechanism is an elimination. We'll come to the eliminations. So I guess we're at the eliminations. Yeah, it's sorry. Yes, absolutely. Thank you, Lauren. There you go. Yep, it's chromium. So what happens here is the chromium trioxide is going to become chromic acid. And again, this shouldn't surprise us. Sulfuric acid is H+. Always react to the most reactive thing in there. That's acid, super strong acid. It's not there to look pretty. It does something. And we have 3 carbonyls. And they're oxygen chromium carbonyl. So if you thought oxygen carbon bond, double bond, was nice and nucleophilic at the oxygen, think about what it does when it's attached to a metal. Okay, that makes sense. And those of you who are taking inorganic chemistry, which as Dr. Drover told me in the hallway yesterday, is definitely the best type of chemistry. He was walking by a student who told him, who was talking to me saying, I'm switching my major because I don't want to do inorganic chemistry. Anyways, we get what the hell's going on with chromium? Why is it making 6 bonds? I'm an organic chemist. I don't have an answer to that question. It's in the D block. That's my answer. That's not a helpful answer. But overall, we've made this chromic acid kind of thing. Okay. Now, we can do a proton transfer. And we're going to put it onto the more basic carbonyl. Carbonyls are more basic than alcohols. And that holds true whether they're attached to chromium or carbon. So we made the active form of the Jones reagent. Now, if we're thinking about it, if that would have been a carbon in the middle, it wouldn't be making 6 bonds, but that carbon would be pretty electrophilic. You're attached to an oxygen with a double bond and it's positively charged. And we can draw a resonance structure with the O neutral oxygen to Cr+. And that's basically what happens. So I'm going to use my alcohol. Put that in green so we can track it. Just going to draw in the hydrogens. We'll see why. And we're going to attack the chromium. So let's just keep track of what belongs to what. And Faith is in there first. You're all right. I am actually missing a carbon. I know she's fast. Oh, well, you're like Mississauga carbons. I don't think I mentioned Texas carbons yet in this class. So you know, carbon makes 4 bonds. We say if a student draws carbon making 5 bonds, we call it a Texas carbon. Both because the Texans think it's because everything is bigger in Texas. The rest of the world knows it's because Texas is insane and not based on reality. So you can take either way, but it's a Texas carbon. If carbon has 5 bonds, it doesn't exist. Okay. So I don't know where that was going. So I don't know what a Mississauga carbon is. It's close to the center of the universe. Or thinks it's close to some place that thinks it's the center of the universe. Right. We can do another proton transfer here. Because just look at how many chromium is making too many bonds. This is making me squeamish, and I'm uncomfortable right now. And I'm just cleaning up the chromium a little bit here. Oops, I'm keeping the chromium in red. So we're back to kind of a normal, like chromium making 2 double bonds to oxygen, 2 single bonds to oxygen. Okay. Now, this is where things get a little bit odd. What happens here is we're about to do the oxidation step. And that's because these two hydrogens have just become very, very acidic. Why? Because on the atom next to it, you've got a really good leaving group. You've got chromium as a leaving group. And so what happens is water as a nucleus, and this is the E2 step. So we grab a hydrogen, we make a double bond, we have a leaving group leave. The leaving group's chromium. And it does like this kind of arrangement thingy to free up its electrons. We'll see why it does that in a second. But it's just an E2. And look what we made. We made an aldehyde. And our chromium is now, this is chromium 4. We started with chromium 6. All the way along here, if you count the bonds to chromium, it's 6. It's always 6. And then suddenly we're going to chromium 4. We've oxidized the carbon, we've reduced the chromium. Oh, for the green proton transfer, this one here, why do we do this? Why do we put it on here? The reason I put it on there is you could have put it on a carbonyl, nothing wrong with that. I can definitely do that. If I put it on that OH though, I can go back to getting 2 carbonyls onto oxygen. So I have put it onto an alcohol, which isn't the most acidic, you're basic, you're absolutely right. What that allows me to do is it allows me to make 2 double bond carbonyls. So we kind of go up to go down to get more stable. Does that make sense, Melissa? Because if I put it on this guy here, and I push the electrons out, I'm going to switch alcohol and carbonyl for carbonyl and alcohol. It's going to be non-productive. It's going to be the same thing. This way I get to push back to reduce the number of oxygens around the chromium back to 4. I think you might understand carbonyls better. I think it's this chromium shit that you don't understand maybe, and that's okay. Okay. Now we're not done yet though, because notice that's an acid. And that's not an acid, that's an aldehyde. And that's because we still have lots and lots of sulfuric acid in water. Now, normally if you mix sulfuric acid, water, and aldehyde, nothing happens. Because if you take an aldehyde, like the one we have here, and you mix that with H+ and water, you protonate the aldehyde. You might even get the acid, that hydrate that we talked about. But, you know, nobody wants to make a hydrate. So yeah, there's an equilibrium, but everything falls back towards the aldehyde because it's much more stable. The difference is if we have a really good electrophile present, we can trap the hydrate, and that's what we're going to do. Because this hydrate is looking around and it sees more Jones reagent. Sorry. Mechanistically, I find a lot of textbooks do actually do what I did earlier because they're trying to save a step and cheat, but it's a lie, and we shouldn't lie. Unless it's really important to lie. This isn't an ethics class. So anyways. We get that intermediate. Now we're going to follow basically exactly the same pattern we just previously followed. Another proton transfer. We don't have 2 carbonyls, do we? Where do I have 2 carbonyls? Well, we start with 2 here. We go to 1. Because we attacked and opened it up. This is just the starting material reagent. We're not using the product of the last reaction, we're using fresh Jones reagent. Like this is more of the starting stuff here. I'm not using this. I'm not using the product. The product consumed is useless. It's just chromium garbage that is really, really expensive to dispose of because it's a heavy metal and it's really toxic. But we got the 1 carbonyl on a chromium because we had to, and it's left untouched. It was there to begin with. There were 2 on the beginning with, now there's 1. If I've still lost you, we can maybe have this conversation orally because I don't know if this is working. Okay, yeah. Okay, so now what we do is actually what we saw last time again. We still have another hydrogen on here. God knows we have water lying around. I'm just going to do the arrows in a different color. It's exactly what we saw last time. So it's thank God it's not a new, or it's still tricky. I completely agree with that. And it's still an E2 elimination, right? Take the hydrogen, make double bond, leaving group leaves. The fact that one of the atoms is an oxygen, not a carbon, doesn't change the fact that it's not that it's an E2 elimination. It's pattern-wise is identical. They need to be anti-periplanar, all that stuff. Now if I draw what I get out of that, I get an acid. And some chromium 4. So what we have here is basically protonating a carbonyl. The carbonyl happens to be on a chromium, but it's protonating a carbonyl, getting a nucleophilic attack on the electrophilic center, which is chromium. Our nucleophile happens to be an alcohol. that turns the chromium into a good leaving group after, a bunch of proton transfers. And then we do an E2 elimination to create the product. Like, each of these individual steps is simple. Combined, it's not simple, but all it is a sequence of steps that each in turn make some logical sense. And then when you string them together, you end up with the chemistry of an aldehyde becoming an acid, or an alcohol in this case, going to an acid via an aldehyde. So the key difference between this and the other reagent that I was pointing out in class, was that if we use PCC, we just went to the aldehyde. Is a chromium-based agent. The mechanism is freaking identical. The only difference between a Jones reagent and PCC is there's no water when you do this with PCC. So you can't make the hydrate. And because you can't make the hydrate, you can't trap a second equivalent of the chromium. And so you can't oxidize to the acid. So PCC is the same thing, except no water, so no hydrate. And instead of oxygens leaving chromium, it's chlorines leaving chromium, but it's all the same. How would we be tested on this on the exam? Two things. I could ask you for this mechanism. I could basically say, here's a reaction, provide the mechanism for this reaction. I could just say, kind of like the assignment, give me a reagent that does this transformation. There's an alcohol, next step is an acid. How does this happen? What do you use? I could give you the starting material and the reagent and say, what's the product of this reaction? Okay, it's Jones reagent. I know what the mechanism is. I don't need to draw the mechanism because he didn't ask for it. I just need to give him the product. So those are all possible ways I could test you on this on the exam. Like if I ask multiple choice questions, which I don't, I could ask, like, in a Jones oxidation, one of the steps involves one of these following mechanisms: E1, SN1, E2, SN2. And the answer would be E2. But I don't ask multiple choice questions on exams. Okay. Anyone have any questions about that, or any questions about something else to do with eliminations or substitutions or radicals? Just opening the floor. We absolutely can, Madison. Do you have a question? And just do some examples if you don't, but. Yeah, hand up, Alyssa.
Hey, I just want to see if we could do an example. So on the first thing that you covered in lecture 25, so the one that we're talking about, you said like there was like a little bit of a difference between the two molecules. I think it was like the reagent was cyanide, and then so they were the exact same things, but one of them had a benzene ring, and then the other one did not. And then you wanted to see which one was faster. Can you just do another example like that?
Yeah, I can't quite think of exactly what the example is, so I'm going to just pull up my slides from when I was teaching that. Lecture 25, you said?
Yep.
Okay, I will go take a look.
Okay, thanks.
Yeah, no, absolutely. Teaching. So it's a good idea to download your stuff so you know where the hell it is from year to year. And I know that, but I don't learn my lessons. There we go, 2300. Extra 25. Marked up. So this is radical stuff, right, Alyssa?
It's right before you started talking about radicals. It was literally just like the exact same molecule, but you had a ring and then it was a benzene ring compared to a non-benzene ring, and then you said which one is like faster.
So maybe it was my last elimination lecture.
It's the elimination slash beginning of.
Yeah, because I just have them nice and clean in PowerPoints. Lecture 27, 25. Okay, I think I found it. Oh, that's what I'm talking about. Zaitsev bases. I have some alkyne examples about that. I don't know if you have a screenshot.
I just sent you a screenshot.
Oh, sweet. Just in a chat or by email?
Just in the chat.
Okay, just unpopulated. Oh, there we go. Oh, okay, yeah, we can definitely do this. Okay, so what kind of reaction is this? By the way, the mixture of cyanide and DMSO is called liquid death because the cyanide DMSO crosses your skin, and if cyanide gets into your bloodstream, it binds to your hemoglobin and kills you in very, very small quantities. Actually, it's kind of surprising how little hemoglobin you need to block up completely to starve you of oxygen and die. So cyanide and DMSO is really, really dangerous. But let's say you're using cyanide and DMSO, and you do these two reactions. And I think the question was basically which one of these is faster. So mechanistically, what kind of mechanism is this? What is the reaction that's happening? Oh, people were answering in the chat. I just wasn't looking at the chat. It's SN2s, right? Right. So exactly. Oh shit! That's it. I probably. Oh, this was the one where I took video and I didn't hit save for the slides, and the slides don't exist. that was not one of my best moments. Okay, so it's an SN2. I completely agree. So in SN2, what determines the speed of the reaction? What factors determine the speed of the reaction? Right. So the strength of the nucleophile determines the speed of the reaction. What else? Because in this case, what we can go is the nucleophile is the same. It's cyanide in both cases in DMSO at the same temperature. So the nucleophile is identical. Accessibility of carbon. Yep. So again, we need an accessible carbon. If you have a tertiary versus a secondary versus a primary, you're going to have differences in reactivity. In this case, the carbon in both cases is a primary. The nature of the leaving group. Oh, could I do something more complicating? Okay, so I did a good job. Good for me. Okay, nature of the leaving group matters. In this case, it's iodine in both cases. What matters here is the strength of the carbon-iodine bond. Because when we say nature of the leaving group, what we're really saying is how strong is that bond. And we often short form it saying it's an iodine leaving group. All iodine leaving groups are the same. They're not, because the bonds can be different strengths. The bond of a carbon-iodine that's adjacent to a benzene ring is weaker than a bond of a carbon-iodine that's adjacent to an aliphatic ring. Aliphatic, saturated, no benzene, no double bonds, no nothing. Aliphatic is just boring. Alkane, hydrocarbon. Well, I guess they're both hydrocarbons. It's a boring hydrocarbon with no double bonds or anything. Sorry, I'm just going to use the term. I just used it, so I will write it. Aliphatic. Boring. So the benzene ring, one adjacent to the benzene ring, is much, much more unstable because if you form a carbocation there, it's stabilized by resonance, and so the carbon-iodine bond is already slightly broken, and so it's easier displaced. And Alyssa's saying, yeah, I get that. Do something harder. Okay, let's do something harder. No, this is a very bad example. I outthought myself and got myself into trouble. Cyanide, DMSO, I guess. One of my guys was actually doing a reaction very similar to this with epoxides. Ooh, let's do epoxides. Yeah, okay, this is a good question now. Yeah, slightly different version of this question. 2. This doesn't actually work, but let's pretend it does. So I touched on this in the lecture notes, and I don't think we've done any examples in class. I guess we're not doing radicals right now. I'm going to break the rule. I told Madison we do radicals, but talk a little bit about the SN2s on epoxides. Okay. Got 4 reactions. Which of these is fastest? Is this complicated enough for you, Alyssa? Let's make the rest of the class cry. Because that's what we all need late November. Okay. Any ideas on which ones are fastest, or which ones you think we're trying to decide between fastest ones? Hopefully we can get there. Yeah. Jeanette's just like, yeah, it's A. You're right, it's A. A is fastest. Well, HCN does exist. It's not. It's a strong acid, actually. It's a pretty. So Melitza, CN's not basic. So HCN is a reasonably strong acid, and that's going to be central to the argument we're going to make. HCN is a gas. It's odorless, colorless, and lethal. Right, Samantha, you're absolutely right. So if you want to take a look at what Samantha says in the chat there. She says A and B are the fastest because the stronger nucleophile, because the nucleophile is charged, everything else is neutral. And A is going to be faster because it's stabilized by more resonance. So there's more of a positive charge able to build up over here because there's more resonance on this side. Now, what's the product? Because I can think of two products. The reason I'm drawing this is we actually opened an epoxide with cyanide today in the lab. It's a really hindered epoxide. I'll just show what we actually opened. Because it actually covers some of the things we've talked about in this course. Nope, that one's also up. So it's got two acetals. It has an epoxide, and it's got the 6-membered ring. And it's really, really hindered because you're going to have to do an SN2 on the epoxide because we use cyanide. And of course, that needs to come in from the top face. But the top face is really, really blocked. Because I've drawn these as if they're sticking out, but they're not. The acetonides, those acetals are sitting right over the ring, and they actually block the angle of attack of the cyanide. This is a really, really hard thing to do because cyanide is a small nucleophile, but there's just no angle. There's no way to get there. So we had to use really, really harsh conditions. So that's why I'm thinking about cyanides and epoxides today. But if we go back to cyanides and epoxides, we've got two products because this oxygen is going to spring open. The epoxide is going to open, but we've got two ways to do it. We can open at this carbon, or we can open at that carbon, because either one could be the electrophile. So let's call the carbons I and II, because we've already used like 1, 2, and 3, and I guess we haven't actually. We could use 1, 2, and 3. But well. It's written now. So which carbon do you think is going to be attacked by the cyanide? I or II? Okay, Christian, keep that in mind. I'm going with Alyssa, less hindered. Less hindered matters a lot. So the positive charge thing with the resonance is a thing. It's real, but it's not going to compensate for being less hindered. So under basic conditions, epoxides always open at the less hindered site. Under, and I'm sure this was in the lecture notes. I know it's in the assignments. I can't spell always. So the product is going to have an OH and a cyanide. The structure in red was relationship between the structure in red and the bottom left in A? Nothing. I'm just talking about why I'm thinking about epoxides. This thing down here has got nothing to do with A. What is the ratio of the statement? It's basic conditions because it's cyanide. II is a less hindered site. Okay, so for B, what do we think? I or II? Perfect. It's not a trick question. There's nothing fancy about here. Yeah, there's double bond instead of a benzene, but it doesn't matter. Hindered, 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 basic, hindered, hindered, basic. Not hindered, I guess. Accessible, basic. Words, salad. Salad. I haven't had lunch today. So salad sounds good. Okay. Yeah. That's exactly what happens. Less hindered. Okay. C. The one thing you should think about when you go to C is you go like, Dr. Trent, there's no strong nucleophile there. You're right, there isn't. But is there an acid? Is there something we can do? And yeah, there is. Is it a super strong acid? No, it isn't. But heat something enough and shit happens. My honors thesis supervisor told me, you know how the Spartans, apocryphally at least, were told to either come back from battle victorious or dead on their shield. So come back with your shield either way. He basically told me the same thing. It's like, I never want to hear that a reaction hasn't worked. You either tell me it worked or you bring me black tar because you heat the crap out of it so much that everything decomposed to shit. Those were his exact words. So heat something enough and it does something or it decomposes to shit. Actually looks like that too. It's this dark black tarry brown stuff. And I'll leave you with that image. So what we're going to do is we're going to protonate the epoxide. Normally, I would actually, if I was going to do this, I would have to add an extra acid in there as well. You can do it with HCN, but I would do it with HCN with a little bit of sulfuric acid or something. Okay. Now, what do we think? I or II and why? Remember, cyanide's a strong nucleophile. It's a weak base. So these are very weakly basic conditions. This isn't strongly basic conditions. These are weakly basic conditions, but even though cyanide's a strong nucleophile. Oh, I will more, all sorts more of that stuff where that comes from, Madison. A font of crude wisdom. Yeah, cyanide's a stick. It is a stick. So that's going to help us with this. So we're switching to I. And you're right, Madison. And the reason why, and maybe you're switching to I because you picked up, it's like, I think there's something different happening here. So I'm going to guess it's the other one now. So what we're doing is if you're thinking about this, go back to several weeks ago when we were talking about bromoniums and iodoniums. and we're talking about, look, the Br plus, you have the I plus, the C plus, and then you have the carbons are positive, but there's a lot more positive charge on a more stable carbon. And if we're thinking about this, big ass delta plus on a secondary carbon, much smaller one on a primary, because primary carbocations suck. And that secondary carbocation isn't only a secondary carbocation, it's a resonance stabilized carbocation. And holy shit, that's good. It's like that's just a great carbocation. So in this case, we built up positive charge. Now in a previous case in the epoxide, there was no positive charge. The epoxide was an epoxide. It wasn't charged. It was neutral. It was all about hindrance because there was no charge. Now there's charge. And negatives just love themselves some positive. So that's what we see is going to happen. And we open at I. So that's kind of cool. So depending on the conditions, if it's acidic or basic, we can open the epoxide at different sites. Now the example I have there down in red actually opens and is controlled by something else because they're both secondaries, they're basically identical. But anyways, this is what happens. And so it shouldn't surprise us that D does exactly the same thing, because of course it does, because although it's not a benzene ring, you still have resonance stabilization and a secondary carbocation. So you get the product. So we're able to introduce the nucleophile at either site on an epoxide by choosing whether it's acting like a straightforward SN2, where we think all about sterics and leaving groups, or if it's acting more like a bromonium iodonium. And we're thinking about the stability of the carbocation on the carbons. So Drake was asking, can I go over why this again? This because if I put a if I've got an OH plus, if I put a carbocation here and make the OH neutral and have a positive charge here, it's a secondary carbocation. It's okay. And it's resonance stabilized by the benzene ring. I can use all those benzene electrons to stabilize it. Whereas if I put the positive charge on this terminal carbon, it's a primary carbocation. Those suck. They're not stable because of hyperconjugation. So secondary more stable because of hyperconjugation. In this case, the secondary is more stable because of resonance. The primary doesn't have resonance and the primary doesn't have hyperconjugation, or not a lot of it. So wouldn't A and B less sterically hinder with the stick no matter what? Yeah. A and B, it doesn't matter if this was a cyanide or a bulkier nucleophile, it would have gone to II in both cases. Because nucleophile, unhindered, attack. A and B are also a whole lot faster because you have a strong nucleophile. Whereas in B and C and D, you have a weaker one because it's HCN. So it has to lose the hydrogen, which it doesn't do all that easily to make the CN minus. You just don't have a strong reason to react. This is probably a better use of our time to talk about radicals anyways today. So Amanda, I covered that mechanism in the lectures. I didn't cover it in these things, and somebody asked me about it, and I just finished eliminations. So Amanda said, why do we do Jones reaction today? Somebody asked about, we had just finished up eliminations, and I think when I was talking about it in this set of lectures, rather than the pre-recorded lectures, I said we come back to it when it's relevant and talking about E2s. If you got it when we did the carbonyl stuff and you went through and went, yeah, I get this is an E2, it's fine. Sweet, good for you. Awesome, then nothing different. Yeah. It's just keeping a promise and answering a question. Okay, it's 2:20. It's Friday. This is like your last weekend that you probably are not desperately studying 24/7. So, you know, enjoy studying 24/5 or 16/7, whatever. So have a somewhat not insane weekend. Try and get some sleep. I'm going to go see my parents, so that's going to suck. But everyone else, have a good time. Yeah, which of these is fastest to say is the answer. Yeah. So under basic conditions, epoxide is always open to less hindered site. Under acidic conditions, just my dad's dying of Alzheimer's, and so it's not a pleasant time right now. I do like my parents; they're good people. Epoxides open via the more stable carbocation. I'm going to change color because it's not going to show up. Okay, take care. Bye, everybody. Okay. Please keep. I don't want to have to delete this lecture again. It's cursed.